I didn't have too much to say. So, okay, the thing is, so it won't take too long, but standard theory does actually apply, it seems to me. So you can compute a p-value because this parameter is kind of out the interior of the parameter space. As an nested model, everything's fine. The problem seems to be that my guess of what's the problem is that you don't have enough data, so the asymptotics aren't kicking in. When you get more data, you should not have too much trouble. And what my advice was going to be, Bayes factors should be too much trouble because there's the dimension of the parameter spaces are similar. The only difference is delta CP, and this has a bounded support. It's a finite range of possible values, so there's not so many choices of prior distribution. What I was going to say, though, is why not compute the likelihood or the posterior distribution of delta CP? I just give you 3 examples here. One's all piled up at pi. One's saying, well, I don't know what the hell delta CP is. And one's saying, oh look, CP violation probably. And there's a lot of information in these likelihood functions. Before you get to the point where you can actually make a discovery, I would really say, these sorts of plots of likelihoods or posterior distributions give you a lot of information.
You were talking about testing your model and fitting parameters.
There you are. I'm sorry.
Fitting parameters. So suppose you fit your model and it doesn't fit, and then you add another parameter and it doesn't fit, and then you add another parameter and it doesn't fit.
Yeah.
You do that maybe 40 times. What's that called?
It's called phishing. So that's why the psychologists are. I mean, it's a lot. I don't really know, but my sense is that it's a lot easier to do that in social sciences because there's any number of variables you can throw in. Insofar as you do it, you want to be very. I mean, every time you do another test like that, that means your p-value is essentially less reliable. So yeah, Nick.
I have a couple comments. The first is dealing with this 5 sigma business.
Yeah.
Now, normally what particle physicists do is do frequentist analyses because they don't like priors and they understand what frequentist is telling you. What happened, as far as I can tell, is that the 5 sigma criteria got introduced simply as a way of taking care of the look elsewhere problem. So if you're searching for a bump, it is unexpected, it makes perfect sense, and it has a Bayesian flavor to it, but we understand at least what's going on. For problems, some of the problems we're dealing with, such as the mass ordering, is simply binary. There is no look order, look elsewhere problem. And so you would think that 3 sigma, which is 99.7%, would be satisfactory for most people. Okay, that's one comment. I don't know if you want to comment, I'll go on to.
Go ahead now.
Okay, now let's go back to the hierarchy. What we have been doing is doing you said there are unknown parameters. That's true. First of all, they're not completely unknown. And secondly, okay, so what we've done in these analyses is do a frequentist analysis, treat the other parameters as nuisance parameters, and then profile over them. So you take the value that's most favorable to the particular hypothesis. And when you do that, for instance, in the NOVA data, you get very little difference between the inverted and normal hierarchy because they have different delta m values. I'm sorry, delta.
Delta
CPs. Okay. Comment?
Yeah, well, let's start with 5 sigma. I'm not sure exactly the history. I had exactly the same thought as you about the look elsewhere effect. Is that why you're doing this, talking to some of the particle physicists? They told me it wasn't. Don't know if that's exactly true. My understanding is there were false discoveries at increasingly higher sigmas, so they kept pushing it up. I agree with you that 5 sigma is kind of a ridiculous threshold, especially when you really have only these 2 models to play with. The question to me would really be, this again, calibration, systematic errors in model misspecification. If you feel that those problems aren't creeping in as much, the problem with them is they're very hard to quantify. But I think that there really should be a real conversation among scientists about what the if you really think 5 sigma is a requirement or not. It's very expensive, you know, to get 5 sigma. And the other thing was, so my understanding is that formally, when you do the profiling, there's no theorem in place that tells you you'll have the normal distribution. On the other hand, I think, you know, every statistical instinct I have says that if those parameters are well, you know them very well from your data, and they don't have much room to wiggle, that you will get something very much like a normal distribution. And it's those other parameters like delta CP, which can be very different under the two models. Whereas so another way to think about it is if the parameter is constrained, that's what I was thinking for, well constrained, and similarly under both models, then I don't think you'll have trouble. If the parameters have very different behavior under the two models, you're on much shakier ground. So that's why delta CP turns out to be problematic. I would still do some Monte Carlo comparisons, even if they're well constrained, just as a sanity check, because the theory really isn't in place, unfortunately. So.
We also usually don't assume Gaussian distributions, but actually do the Monte Carlo. And that's we're not in the 5 sigma region, so we don't have to worry about the statistics as much.
The theory, yeah, that's right.